Assalamu alaikum wa rahmatullah. In this video, we are going to start with Kinematics 2 Part 1. At the end of Kinematics 2, you will be able to define the curvilinear abscissa of a moving particle, define the angular abscissa, angular velocity, and angular acceleration in circular motion, relate the curvilinear and the angular quantities, and determine the characteristics of the uniform circular motion. In this part, only the first three objectives will be covered. Before, let's remember the main ideas of the previous chapter. Acceleration is the rate of change of the velocity vector over time. In the reference tangent normal, the acceleration vector is equal to at vector plus an vector, and their magnitude is related by a squared is equal to at squared plus an squared. At is the tangential acceleration, and its magnitude is given by the derivative of the speed. An is the normal acceleration, and its magnitude is equal to speed squared divided by r, where r is the radius of curvature, and the velocity vector is equal to vut, where v is equal to radical vx squared plus vy squared. Let m be a particle describing a curvilinear path. Its position is determined by the curvilinear abscissa S of t. To define S of t, three steps should be followed. 1. Choose an origin I. 2. Orient the trajectory in a chosen positive direction. 3. The curvilinear abscissa is the length of the arc IM, which is defined by S of t. Pay attention that the curvilinear abscissa is an algebraic measure. For example, if M has a curvilinear abscissa S of t is equal to 2t squared plus t minus 2 determined as 0, we have to substitute t equal to 0 in the expression of S of t, and that will give minus 2 meters. M starts from the left side of I as indicated on the figure. Variation of the curvilinear abscissa delta S. The variation of the curvilinear abscissa delta S between two instants t initial and t final is the algebraic measure of the distance covered by the moving particle during the time interval delta t tf minus ti. For example, a particle m moves on a circle of radius 7 meters with a curvilinear abscissa S of t is equal to 2t squared plus 2t plus 3. Determine the distance covered by the particle during the first 3 seconds, then deduce the number of turns that m covers during this duration. Keep in mind that if m describes a circular path of radius r, then it covers 1 perimeter in 1 complete turn. 1 perimeter means 2 pi r. Substitute first t is equal to 0 seconds in the expression of S of t, and that will give 3 meters. We plot m0 on the figure, and S at time t is equal to 3 seconds is equal to 27 meters, and we plot m3 on the figure. Now, delta S, which is the variation of the curvilinear abscissa, is equal to S of 3 minus S of 0, which is equal to 24 meters. The perimeter of the circle is equal to 2 pi r, which is 43.9 meters. Now, by comparing delta S and the perimeter, we find that 24 meters is less than 43.9 meters. Then we deduce that the particle covers less than 1 turn. Application number 1. A particle m moves along the circumference of a circle of radius r is equal to 2 meters. The curvilinear abscissa of m is given by S of t is equal to t squared minus 2. SI units are used for t and for s. 1. Calculate S at time t is equal to 0 seconds. We substitute t equal to 0 in the expression of S of t to give minus 2 meters, and that means m doesn't start from the origin as you can see in this figure. Part 2. Determine the time needed by m to complete the third rotation. First of all, we have to calculate delta S, which is t squared. To complete the first 2 rotations, that means 2 perimeters. Delta S should be equal to 2 into 2 pi r, which is equal to 8 times 3.14, which is equal to 25.12 meters squared. Now, substituting instead of delta t squared and solving the equation will give t2 is equal to approximately 5 seconds. That means the first 2 turns has taken 5 seconds approximately. What about the third turn? To complete the first 3 rotations, delta S should be equal to 6 pi r, which is equal to 37.68 meters. By solving this equation, we find that t3 is equal to 6.13 seconds. Now to find the duration of the third rotation, we have to subtract t3 minus t2, which is 1.12 seconds. After defining the curvilinear abscissa, let's now define the curvilinear quantities. First, the average velocity. It is the rate of change of the curvilinear abscissa with respect to time. V average is given by delta s divided by delta t. Its unit is meter per second. The linear velocity is the limit of the average velocity as delta t tends to 0, which is equal to the derivative of the curvilinear abscissa with respect to time. The tangential acceleration is the derivative of the linear velocity with respect to time, and its unit is given in meter per second squared. Pay attention that v is the algebraic quantity of the linear velocity. Then the derivative of the linear velocity gives at and not the acceleration vector. Application number 2. In a curvilinear motion, the time equation is s of t is equal to 4t squared minus 2t plus 1 SI units. Determine the magnitude of the acceleration vector at t is equal to 1 second, knowing that the radius of curvature at this instant is 9 meters. To find the magnitude of the acceleration vector, we have to use this relation, a squared is equal to at squared plus an squared. First of all, find v, which is the derivative of s. It is equal to at minus 2. We substitute t is equal to 1 second in v to give 6 meter per second. We find at, which is the derivative of v. It is equal to 8 meter per second squared. Now we find an at time t is equal to 1 second is equal to v squared divided by r, which gives 4 meter per second squared. We substitute now in the first equation to find that a squared is equal to 80, and therefore the acceleration is equal to 9 meter per second squared. What is the angular abscissa? Consider a particle moving on a circle of radius r and center O. The positive sense here is chosen to be anticlockwise. This particle moves from point A, which is taken to be the origin of the circle, to point M, where it covers an angle theta. We define the angular abscissa, which is equal to theta, the measure of the angle AOM relative to the origin A. Theta is given in radians. Then, the angular abscissa is given by theta, which is equal to AOM. The angular velocity is equal to the derivative of theta and given in radians per second, and the angular acceleration, it is the derivative of theta prime, and it is given in radians per second squared. Application number 3. The angular abscissa of a particle moving along a circular path is given by the following time equation. Theta of t is equal to 0.1 t squared plus 0.5 t. Theta is given in radians and t in seconds. Part 1. Calculate at t is equal to 2 seconds the angular abscissa, the angular velocity, and the angular acceleration. To find the angular abscissa, we have to substitute t is equal to 2 seconds in the expression of theta, and that will give 1.4 radians. To find the angular velocity, we have to find first the derivative of the angular abscissa, which is 0.2t plus 0.5 given in radians per second. Now we substitute 2 in the equation of theta prime, which will give 0.9 radians per second. To find the angular acceleration, we find the derivative of the angular velocity, which is 0.2 radians per second squared. It is constant and independent of time. Part 2. At what instant does the particle finish its first turn? We know first of all that theta 0 is equal to 0 radians. Then this particle starts from the origin. Therefore, to finish its first turn, theta of t should be equal to 2 pi radians. By solving this equation, we get two solutions. The first one is t1 is equal to 5.811 seconds, which is accepted, and the other one will be negative and rejected. Now let's find the relation between the angular and the curvilinear abscissas. If a particle m moving on a circle of radius r describes the whole circumference of the circle, then it is moving a distance which is equal to the perimeter 2 pi r in meters, and this corresponds to an angle which is 2 pi in radians. If this particle covers an arc S in meters, then it has covered an angle theta in radians. When cross multiplication is applied, we find that theta is equal to S divided by R. Then, S is equal to R theta. This is the relation between the angular and the curvilinear abscissas. Pay attention that theta and s have the same sign that depends on the positive sense. Now to find the relation between the angular velocity and the linear velocity, we have to derive both sides of this equation. S prime is equal to the derivative of r theta, and knowing that r is constant, then this derivative will give v is equal to r theta prime. Now to find the relation between the tangential acceleration and the angular acceleration, we also derive both sides of this equation. V prime is equal to the derivative of r theta prime. Knowing that r is constant, it will give at is equal to r theta double prime. Now try to show alone that an is equal to r theta prime squared. Application number 4. A particle moves on the circumference of a circle of radius r is equal to 10 centimeters. The angular time equation is theta of t is equal to 2t squared plus 4t plus pi divided by 2 SI units. Part 1. Determine the curvilinear abscissa S of t at an instant t. To find S of t, use the relation S is equal to r theta, and this will give 0.2 t squared plus 0.4 t plus 0.1 pi divided by 2. Part 2. Determine v, then theta prime. To find v, we find the derivative of s, which is 0.4 t plus 0.4 meter per second. But we know that v is equal to r theta prime, then theta prime is equal to v divided by r, which is 40 plus 4 radians per second. Or we can find theta prime using the derivative of theta. Part 3. Determine theta double prime then at. Theta double prime is the derivative of theta prime, which is 4 radians per second squared, so at is equal to r theta double prime, which is 0.4 meter per second squared. Part 4. Calculate the number of turns at t is equal to 2 seconds. Using the relation n is equal to theta minus theta 0 divided by 2 pi, we substitute t in the expression of theta of t, that will give 16 plus pi over 2 radians, and we substitute t is equal to 0 seconds in the equation of theta, and that will give pi over 2. Then theta minus theta 0 is equal to 16, therefore n is equal to 2.54, that means approximately 2.5 turns. Let us now sum up. 1. The curvilinear abscissa S of t describes the position of a particle in a curvilinear path. 2. The average velocity is given by delta S divided by delta t. The linear velocity is the derivative of the curvilinear abscissa S, and the tangential acceleration is the derivative of the linear velocity. 3. The angular abscissa is given by theta, the angular velocity is given by theta prime, and the angular acceleration is given by theta double prime. 4. The curvilinear and the angular quantities can be related through S is equal to r theta, V is equal to r theta prime, at is equal to r theta double prime, and an is equal to r theta prime squared. It's the end of part 1 of Kinematics 2. Thank you for watching.